I can append 3, and that's still a prime. And I can append another 3, and that's still a prime. And the same question can be asked for square free numbers and Fibonacci numbers. And this summer, we have proven that it is impossible to walk to infinity in Fibonacci sequence, but we couldn't have a direct proof for prime and square free numbers. So instead, we use some stochastic models to explain the behavior of their walks. And still, when we only consider primes in base 2, 4, or 5, we could also show that it is impossible to do so. And also, the longest prime walk we could find is of length 11, which is pretty big. And next slide.
So first of all, when we started the project on square free numbers, we came up with a couple of conjectures that we could disprove computationally. So first of all, most of you should be familiar with what a square free number is. It's just an integer that's not divisible by any perfect square other than 1. And we define a number to be non-square free extendable in base B if by appending any digit to the right, well, we get a non-square free number. Similarly, a right truncatable square free number is a number that remains square free when the last digit is successfully removed. So without further ado, these are the conjectures we disproved computationally. So there's no square free, we conjectured that there's no square free number that's not square free extendable, and also that there's no non-square free extendable number that's also right truncatable square free in base 10. We computed, our program came up with this large number that showed that this is a right truncatable square free number that's also a non-square free extendable number. And for left appending, it came up with this huge number as well. In particular, this is really interesting because it means that it is possible to start with an empty string and just append digits to the right randomly and stay square free at all times until we reach a time where there's no digit we can append. So we have to reach an end.
Okay, so this part of the talk is going to be on stochastic models of prime walks. So we had to use, we thought it would be very tough to prove anything about the primes definitively when it came to appending digits because it hadn't been studied before. So we first looked at it stochastically, so random models of prime walks, so appending digits to primes. So PNT states that the probability, or the number of primes up to n is n over log n. So the probability that some number up to n is prime is 1 over log n. So the formula below, it states that the expectation of our walk length is going to be equal to n times the probability the walk has length exactly n, summed up from n to infinity. And we proved that that was equal to the sum of the probability that the walk had at least length n. And we could solve for that expression, and which is the thing on the left. So we're taking the probability that we're taking 1 minus the probability that all the numbers that we try to append are composite. And then we're taking the product of all those up to some number n. So another manipulation we can do on the expression is to find the expected value or the expected value of the walk length up to some number with s digits in base B. And so that's just that formula. And so we get this table here, and you can see that we have base 2, 3 up to 10, and then 10 is our refined walk, which I'll get to in a second, but you can see all the lengths of the expected values of the lengths of the walks in the table. So here are a bunch of tables for you to look at. the refined greedy model is, well, the greedy model is what I just said before of, okay, let's take any number, append it, and see what the probability is that it's a good walk. Refined greedy model is we're just taking into consideration some modular arithmetic things. Like in base 10, we will only add like the digits 3 and 9 to the end of the digit because we don't want to 1, 3,
7, and 9, yeah.
1, 3, 7, and 9. And yeah, so those are the values for that. And then we also computed the frequency of added digits and prime walks at starting point less than 1 million. As you can see, adding 1s and 7s are less likely to give you a prime walk because you can't add more than one of them in base 10. And then the table of expected value of the walks with starting point to mod 3. So then we considered what would happen if you were allowed to add a digit anywhere inside a prime number. So given like 23, not just adding a digit to the end of it, but maybe adding something like in the middle. So all we had to do to adjust our previous expression was find the possibilities for the number of ways you could add a digit into a number, or add a digit into a number, yeah. And so we evaluated this for n up to n is equals 1000 on the very left. And as you can see, for base 10, starting at 1 digit, we have an expected length of almost 62, which is pretty large. So it proved pretty hard to find, to compute like these very long walks, but one example that we found of length 17 is as follows. So computing the limit, we find that the expected walk length is not bounded as base increases. So we conjecture that it seems very likely that a walk to infinity is possible by adding a digit anywhere. And then just for fun, using the Miller-Raven primality test, we see that walks of over length 100 in base 10 are extremely common. We found a bunch of examples of walks of length 100, but they're not really examples. We just expect them to be correct within a very small margin of error.
All right, so going back to square free numbers, I'm going to present the behavior model for it. So first of all, even though the project started with primes, we immediately thought that it was impossible to walk to infinity using primes. And one of the main reasons for this is because primes have density that tends to 0 as n goes to infinity. On the other hand, as you can see, the density of square free numbers goes to 6 over pi squared as n goes to infinity. So using this, we can assume that the probability of x being square free is just 6 over pi squared. Furthermore, using this, we computed that the expected number of steps in our random square free walk is going to be around 1.55. However, when we start with small values, intuitively we should have longer walks as the primes are sparse and there's more square free numbers. And by running a model, we saw that the expected value when a number when we start with a number between 1 and 100 is 1.75. When we start with a number between 1,000 and 100,000, the expected value tends to 171. And then when we start with a number between 100,000 and 10 million, the expected value tends to 1.69. And lastly, when we start with a number between 10 million and 100 million, the value is 1.52. Lastly, we compare the frequency of the digits added in square free walks. And as you can see, just by looking at this table real quick, the odd digits appear more frequently than the even digits, and 5 doesn't appear as often as the other digits, and so on. From a number theory point of view, this is why this happens. So odd digits appear more frequently than even digits because if x is square free, then it cannot be a multiple of 4. So which is the smallest smallest square that's not 1, right? On the other hand, the frequencies of 2 and 6 are less than the frequency of 0, 4, and 8. Again, this is by modulo of 4 consideration, because if x is odd, I is 0, 4, or 8. And on the other hand, if x is even, then I can only be 2 or 6. But x is almost twice more likely to be odd, so the frequency of 0, 4, and 8 is larger than that of 2 and 6. Furthermore, 5 appears less than any other odd digits, again by modulo 5 and 25 considerations. Lastly, 9 appears more often than any other digit. This is because if x is square free, then x cannot be divisible by 9. So then x, by appending 9 to the right, we get a number that's not congruent to 0 modulo 9. And as the starting point increases, the frequencies tend to stabilize. So now we're going to talk about some proofs in prime walks and Fibonacci walks.
Okay, so one theorem that was proved this summer is that it is impossible to walk to infinity on primes in base 2, 4, and 5, appending to the right by 1 digit. So here's an example of a proof we got for base 4. So we only consider appending 1 or 3, and appending 1 to a prime, that's 2 mod 3, will give you 0 mod 3. So one can append 1 at most a single time in walking to infinity. So we consider what happens when you add only, or append only 3 to some digit in base 4. And it ends up that you get this formula for the digit pi equals 4 to the I minus 1 times p1 plus 4 to the I minus 1 minus 1. And then by Fermat's little theorem, 4 to the p1 minus 1 is congruent to 1 mod p1. So we can factor that out and see that the whole expression is divisible by p1. So it's impossible to walk to infinity.
And another interesting problem about prime walks is if we could walk to infinity, given we are allowed to append unbounded number of digits. So for the left appending, it is known that it is possible to construct an infinite prime walk by appending unbounded number of digits to the left. And we can easily prove this theorem using the Dirichlet theorem on arithmetic progression. However, our interest is in the counterpart of this theorem, which is the right appending case. And we have shown that it is possible to construct an infinite prime walk by appending unbounded number of digits to the right. And here is our proof. So basically, if we have a prime p, then we want to show that there exists an n such that there is a prime between this interval. This is because when we append n digits to the right of p, that newly appended number will be in this interval. And then with some algebraic manipulation, we could find that given fixed p and r, we could find n such that there exists x greater than some constant, and this interval lies entirely in the interval that we are interested in. And according to the work of Baker, Harman, and Pins, they show that there is a prime in this interval. And that completes our proof because it shows that there is a prime in this interval in the p times 10 to the n to p plus 1 10 to the n interval. And the last number theory sequence that we haven't talked about is Fibonacci numbers. And we ask the same question, which is, can we append at most n digit at a time and obtain a walk to infinity? And the answer to this question is no. But before we prove our main question, here are some lemmas and theorems that we found along the way. So the first two lemmas here are some observation on the relationship between Fm and Fm plus k. And these two lemmas leads us to this first theorem, which is appending exactly 1 digit at a time. And we proved that it is impossible to do so. In particular, all such walks have lengths at most 2. And similarly, for the appending exactly n-digit case, we also found that it is impossible to do so. And in particular, any appendable step must be less than some constant. Next slide. And both theorems led us to our main question, which is when we are allowed to append at most n digits each time. And we found that the length of the longest walk is at most floor of log base 2 of n over n naught plus 2, when n naught is the number of digits of the starting Fibonacci. And here is our proof, but in the interest of time, I think I will have to skip the proof for now. Next slide. In conclusion, we have mainly studied 3 number theory sequences: prime, square free, and Fibonacci. And while in some cases we could prove or disprove that there is a walk to infinity, other cases haven't yet been proven. However, with the help of our stochastic models, we now have a strong inclination of what should be the answers to those cases. And that's all we have. So thank you so much for joining our research talk.
Yeah, thank you so much. There's also a talk by another polymath RU group that studied similar walks in number fields. So please tune into that later on today.
Great, thank you. Any questions for the speakers? So I have a question. Maybe you said this, but maybe, so do you get some sense of where the boundary is? So on your previous slide, you discussed some you believe to be possible, some you believe to be impossible. It was like the one just before this, I think. Yeah. I guess, do you have, it seems like you could generalize, your work a huge amount to cover all sorts of sequences. And do you have any sense of where the boundary lies?
Not really. We try to like look at sequences that have density, between 0 and 6 over pi squared, right? Like sequences that have density in between primes and square free numbers, but we couldn't really get anything interesting and anything worth mentioning.
Mm-hmm.
Ploy actually worked on cube free numbers and fourth free numbers. But these have density larger than square free numbers, and we came up with some results. Do you want to talk about that for a bit, Ploy?
So for fourth free and cube free numbers, we have found that the density of them are bigger than the square free numbers, because it's just 1 over the zeta function of that exponent. And we not really found anything in particular, except that the expected walk length is greater than that of square free.
Okay, thank you. Other questions? Okay, so if there's no further questions, let's thank our speakers again. I'll stop the recording.
Thank you so much.